So now what we're going to look at is finding the zeros of polynomials whose lead coefficient isn't necessarily 1. So for example, we have some polynomial p of x. It's something x to the n plus something x to the n minus 1, dot, 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 something x plus a constant. So if all of those somethings, all of those coefficients are integers, then the rational zeros of this polynomial, so they're going to look like are actually fractions, so something like b over c, but they're going to have a really particular form. So just as with the monic polynomials, the top is going to divide the constant term, that a naught in my polynomial, and the bottom, the numerator, is actually going to divide the lead coefficient, so that an. This is completely consistent with the first part of the theorem, because if that an is 1, if the polynomial is monic, then the only number that goes into 1 is 1. So that c on the bottom there, so that c is actually just 1. And then we have an integer. So it is completely consistent. It's just this is a little bit of an extension. And it is a little bit more work to get these answers, but it's kind of in line with the fact that factoring a polynomial, a quadratic polynomial whose lead coefficient isn't 1, is a little bit more challenging. So that's going to be our first example. This p of x equals 8x squared minus 10x minus 3. So we can do this without really using that theorem at all, but we're just going to make sure that the result is consistent with the theorem. So old school factoring methods here. I want two numbers that add to -10 and two numbers that, these Christmas colors, are going to multiply to 8 times -3 is -24. So a difference of 10 and a product of 24 should be 2 and 12. And one of them's got to be negative to get the -24, and it's got to be on the 12 so that they add up to -10. And so I'll do this a long way. 8x squared plus 2x minus 12x, right? So remember, that's just the split, the 2 and the -12. And then -3, do my group factoring. I can take out 2x from the first two. And that will leave me with 4x plus 1. And then I can take out -3, and that should also leave me with 4x plus 1. So they both have a 4x plus 1. That means I've done this correctly. So I can take out the 4x plus 1, and then I'm left with 2x from the first term, -3 from the second term. And so if this is equal to 0, then that means that I get 4x plus 1 is 0, so x is -1/4, or 2x minus 3 is 0, which means that x is 3/2. And so these are our two zeros. And what we can do now is just make sure that this is consistent with the theorem that I've said here. So if I look at the first one, so -1/4, it doesn't really matter where we put the 1 because it doesn't affect divisibility. But if we look at the way that this is written here, so this is my an, and -3 is my a naught, the constant, right? My lead term is 8, my constant is 3. So 1 is a factor of 3. Well, I mean, technically a naught is -3, but that doesn't really matter for what we're doing right now. Yeah, so 1 is a factor of -3. 4 is a factor of 8, right? Believe me? I hope so. And then if I look at the other one, 3/2, well, 3 is in fact a factor of 3, -3. and 2 is indeed a factor of 8. And so yeah, so this seems to make sense with the theorem. And so just for the next couple examples, what we're going to do is look at how we use this theorem. So I'll go through pretty much the same types of questions as I did with the monic polynomial. Okay, so for our second example, we're going to have this polynomial. P of x is 12x4 plus something plus 10. And we're going to list all of the potential rational zeros from this. So just as before, what we'll do with our list is do this list, the potential rational zeros. I'm just going to shorten it. And so what we can do is set this up as a plus or minus. And then the list on the top will be factors of the constant. So in this case, it'll be the 10. And then divided by factors of the lead coefficient. So in this case, it'll be the 12. Right, and again, if the lead coefficient was 1, it would just be 1 on the bottom. So we wouldn't really have anything. We would just have 1. And so what we've got to do is just list them all, plus minus. So my factors of 10 are 1, 2, 5, and 10. And 12 will be 1, 2, 3, 4, 6, and 12. And so what we can do now, I need to actually make them. They should all be these nice rational numbers. So what I'm going to do is list them. I'm going to raise that a little bit so I have a bit more space to draw a last line. So what I'm going to do is just kind of make my way from left to right. Maybe I'll start with everything over the 1. So I'd have 1 over 1, 2 over 1, 5 over 1, 10 over 1, and then make my way over to the 2. And I have to go through everything on the top over the 2. It's going to be a really long list. 1 over 2, 2 over 2, 5 over 2, 10 over 2, and go to the next one, the 3. 1 over 3, 2 over 3, 5 over 3, 10 over 3. So, I mean, don't worry, I'm not going to ask you to test all these in practice. That would be a little bit absurd. And even writing out a list, like this is probably the longest one you're going to see. I just did all the 4s. There's 2 more sets. I need the 6s and the 12s. 1 over 6, 2 over 6, 3 over 6, 10 over 6, and 1 over 12, 2 over 12, 5 over 12. Oh, I made a mistake there. I'll go back and fix it. And 10 over 12. Let me just, yeah, so I wrote a 3 over 6. That should have been a 5 over 6. Let me just write it in this red color so it's a little more visible. So yeah, that one should be 5 over 6. There is actually a lot of repetition in this list, and it's actually pretty easy to find. Anything in this list that's not in lowest terms would have already shown up already. So I'm going to rewrite the first few. Those are just integers, 1, 2, 5, and 10. And then a half is in lowest terms. 2 over 2 is not in lowest terms. And you can see it's already written there as 1. So I don't need to rewrite it. I can just cancel that one out. 10 over 2 is actually 5 over 1, which is already there. If I make my way across, 2 over 4 is a half, which I've already got. 10 over 4 is 5 over 2, which I've already got. 2 over 6 is a third, which I've already got. 10 over 6, 2 over 12, and 10 over 12. I've actually already got all of those ones just by reducing their terms. So I'm just going to list the ones that I actually do have here. 5 over 2, 1 over 3, 2 over 3, 5 over 3, 10 over 3, 1 over 4, 5 over 4, 1 over 6, 5 over 6, 1 over 12, 5 over 12. So yeah, don't expect to have to write out a list quite that long. mostly I just wanted to do a bigger one so that you could see some of the cancellations that take place, and some of them might simplify to just integers, but this would be the whole set. If I actually asked you to factor this polynomial, I would be pretty much a terrible person, because you'd have to go through and test a bunch of these until you start finding zeros. And that, especially when you get into those fractions, is not particularly enjoyable. So that would not be kind of me, but we can do one example where we can actually go through and find all the rational ones, and it won't be that bad. All right, so for this last example, we are going to find all of the zeros of this q of x polynomial, 6x cubed plus 7x squared minus x minus 2. So the way that we get this started, first, again, list all the potential rational zeros, which will be factors of the constant 2 or negative 2 divided by factors of the lead coefficient, the 6. So plus or minus, factors of 2 are just 1 and 2. Factors of 6, 1, 2, 3, and 6. And so I'll write out my bigger list here. I'd have 1 and 2, so 1 over 1, 2 over 1, 1 over 2, 2 over 2, which is 1, which I already got, so I don't need that. 1 over 3, and 2 over 3. And 1 over 6, and 2 over 6 is not in lowest term, so I should already have it. Yeah, so it would be my list of 6 things there. So yeah, I just as before, plug them in until I find something. And that's how we're gonna do this, and hopefully it's not too bad. So I'll do a q of 1 is 6 plus 7 minus 1 minus 2. That's too big. I know that's greater than 0, so I'll use my little sad face there. Q of negative 1 is negative 6 plus 7 plus 1 is the double negative minus 2. Yeah, so I've got plus 8 minus 8. That one is a 0, so that's good. It is third degree, so I know I can stop at 3, but I've only got 1 so far. Let's try the 2's. Q of 2 is, what's that, 6 times 8 is 48 plus, you can just do this on a calculator. That's all right. 7 times 4 is 28 minus 2 minus 2. That is definitely bigger than 0. And q of negative 2, so that should be negative 48 plus 28 plus 2 minus 2. That should be, I think, negative 20. So that is definitely not 0. Keep trying. So let's try q of a half. It does start to get a little ugly with those fractions, but I'll manage. Q of a half, so that's going to be 6 over 8 plus 7 over 4 minus a half minus 2. So if I work that out, that should be, what is that, 3/4 plus 7/4 is 10 over 4 minus 2 over 4. I don't think that one works. I wish I had a calculator handy. I'll just rewrite it. So yeah, 3 over 4, 10 over 4, minus 2 over 4. So that's 8 over 4. Oh, yeah, that's right. 8 over 4 minus 8 over 4. That is, in fact, 0. So that one's good. Q of -1/2 will be -6/8 plus 7/4 plus 1/2 minus 2. And that looks to be, that could be close. Maybe I'll double check my work here. So -3/4 plus 7/4 plus 2/4 minus 8/4. And yeah, that's not quite going to be it. I think that's -1/2 or -2/4. So that's no good. I'll just say it's not 0. What do we get for the next one? 1/3. So I get, maybe I'll try to clean this up a little bit as I go. So 6/27, which is 2/9 plus 7/9 minus, so I'm just going to write this over 9. So minus 1/3, which would be 3/9, and then minus 2, which would be 18/9, and that definitely looks too negative. So it gets a sad face, and -1/3 should be -2/9 plus 7/9 plus 3/9 and minus 18/9. And what does that give us? Definitely, again, too negative. Sad faces are getting worse every time. I might have to go all the way to the end of the line here. So if you're annoyed by how long this is taking, that's kind of good, because the last lesson is going to be just a few tricks that we can use to shorten the work. So Q of 2/3, so what are we going to get? 8 over, should be, if I reduce this, 16/9. Yeah. And then plus, so 7 times 4/9, which would be 28/9. And then minus 6/9. And then minus 18/9. That looks too big. And Q of -2/3. Fortunately, I do have the numbers already worked out. I'm going to double check them as I go, though. 48 divided by 3, yeah, so -16/9 plus 7 times 4/9 minus, so it'd be plus 2/3, which would be 6/9, and then minus 2, which is 18/9. And that actually looks like I get 34 and 34 for the positives and negatives. That is 0. I've got my 3. I said I do only need 3. And I've got them. I've got my -2/3, my 1/2, and my -1. So my zeros are in that list. So x is, let's say, -1, 1/2, and a -2/3. And if you recall from how we would list those factors, we can actually get an idea of how the factorization would go. We could actually put this together. Q of x, not p, is going to be, so I get x plus 1 from the first one. The other one, the 1/2, is actually going to be 2x minus 1. Right, so it would be like x minus 1/2, but I want to get rid of that ugly denominator. And then the last one is going to actually give me the 3x plus 2. So that's going to tell me the exact factorization of this, and you should be able to actually check, if you were to multiply this out, that we would get Q right back out. And so I'm just kind of using a little bit of how we do that factorization. Hopefully what you're noticing is that as soon as I get one of them, I know a factor that comes out from Q, so why don't I just factor it out by dividing? And that's long division. Because once I factor it out, for example, if I know that x plus 1 is a factor, then what's left is a quadratic, and I can use much easier techniques to find the roots of a quadratic than plugging in 7 or 8 fractions and working those out. So that's how we're going to sort of put all of this together and hopefully save a little bit of time and come up with more efficient ways of doing this. You'll also notice that the examples I gave here, I said, well, I did actually say here, find the zeros of Q of X. I didn't just say find the rational ones. So if we had only found one solution in this whole set, then there might actually be irrational ones, and we'd have to use other techniques to find them. Also, something might get repeated, which is also a little bit of an issue that doesn't really show up in this method. So it's not this method isn't great. So we're going to find better ones.